Okay, thank you, Julien. Okay, so, well, first, thanks for the organizers and everybody to be there at 9 something in the morning of the first day. Okay, so I will talk about the, as my title says, the Thue choice number, which is a problem which I find interesting and which is a good motivation for what I really want to talk about, which is this counting argument, which is a proof technique that I like. I think some of you might already have heard me talking about that in other events, but still, so my goal really is to talk about this counting argument, and the Thue choice number is going to be my motivation to talk about these arguments today. Okay, so let me recall some definition that not all of you might be familiar with. So what I'm going to call a square is simply a word of the form UU, where U is non-empty, and then I'm going to say that the period of my square is just the length of the part which I'm repeating. And I'm going to say that the word is square-free if none of its factor is a square. So for instance, ABC is a square. The following word is not square-free because it contains the square BC as a factor. And this one is square-free. You can check that none of the factor is a square. Okay. So that's notion of square. So let me remind this theorem, which is a result from Thue in 1906, that says that by using only 3 different letters, you can make an infinite sequence which does not contain any square. Right? So there is arbitrarily long square-free words over 0, 1, 2. And this result is often considered as the starting point of combinatorics on words, one of the first results of combinatorics on words. So naturally, it's been generalized in many directions. I'm just generalized and variation of it have been studied. So I'm just giving some of them now. So a lot of them in combinatorics on words, obviously. There is some I'm mentioning at the end which are not in combinatorics on words. Like for instance, there is this notion of non-repetitive colorings of graph, where the idea is you want to color a graph such that there is no square that appears on the coloring when you look at the path. So this has been generalized in really many directions. And one more direction that I want to mention today is this one, which I'm going to explain in the next slides. But yeah, so it's going to be a generalization of this old result from Thue. And so for this, I'm going to look at a slightly different setting than the one we usually use to for this kind of question, which is I'm not going to have one alphabet. Like usually we have one alphabet and we say, okay, can you avoid something over words over this alphabet? Now we'll have a slightly different setting. I have a sequence of alphabet. So at every position, I have a different alphabet, and I want to build a word such that my ith letter comes from the ith alphabet, right? So for instance, and I will, if, in particular, if my word W is infinite, I will just write that W belongs to the product of my alphabets, which makes sense. So for instance, I have a sequence of alphabet, and I want to build a word that respects the sequence of alphabet. Well, I can do this. 0 indeed comes from the first alphabet, 2 comes from the second alphabet, etc. So it's just a generalization of this setting that we are used to in combinatorics and words. Okay. And again, I told you that what I want to do is to avoid squares. So this is what I want to generalize. So, okay, maybe just, so the question for me would be, okay, now given a particular sequence of alphabet, can you build a word which avoids squares over this particular sequence of alphabet? So the first thing you might want to look at is something related to the size of these alphabets. So in particular, can you find, a value, an integer k, such that if all the alphabet are of size at least k, then you can build an infinite square-free words which respect the sequence of alphabet. And if such a k exists, I'm going to call it the Thue choice number, right? The smallest such k. Okay, so little bit about this. Maybe the question might sounds a bit weird. In particular, somehow intuitively, when you think about squares, it feels like if consecutive alphabets are different, then it should be easier to avoid squares, right? Because, well, I mean, if I don't have the same letters into consecutive position, then it's going to be easier to choose letters which are different, right? So there is this intuition that somehow the worst cases should be when all the alphabets are identical, so then you should be able to take the value 3. We shouldn't trust this intuition. Maybe it's true, but we shouldn't believe in this intuition, and I just want to illustrate this in the next slide, so I will make a small detour by graph coloring, where this is one of the motivations of this question, so I want to make this small detour. So there is this notion of proper coloring of graph, where proper coloring of a graph is just I want to give colors to a vertices such that adjacent vertices do not receive the same color. And so in particular, if I look, for instance, at this graph, then I can properly color it with 2 colors as such, right? This is a bipartite graph. Now I want you to look at the same generalization of the question, which is called least coloring, which has been studied a lot by people from graph theory. So I'm giving 2 colors to each vertices, and now I want to find proper coloring of this graph which respect this list. And so somehow the intuition should be even stronger there, right? Because now, I mean, clearly if adjacent vertices have a different list, then it should be easier to color, right? Because I just want that adjacent vertices receive a different color. So it should help me. However, if we look at this particular choice of list, actually it's not possible to provide a proper coloring. So how can you do that? Well, first look at the vertices on the left. For instance, if they take the color green and yellow, then I cannot color the vertex on the top right. Now, if they take green and red, then you cannot color the second vertices on the right. If they take blue and yellow, you cannot take the third one. And if they take blue and red, you cannot take the last one. And this example is really easy to generalize to lists of size k. You have k vertices on the left. You have k to the k vertices on the right. You need only 2 colors to properly color, but you cannot do it with list of size k. So somehow there is a really big gap between what you can do when the set is the same everywhere and what you can do when you just know that the size of the set is at most something. Yeah, so really the point of this data was to say, do not trust your intuition for this. Your intuition is bad. I mean, at least my intuition is bad. I don't know you, but mine is bad. Okay, so let's not talk about graph coloring anymore. Still, I can prove something, which is that if all of my lists are size at least 4, then I can build a square free word. Right, so this is what I'm going to prove, that I have my sequence of alphabet, all the alphabet list of size at least 4. Yeah, oh, by the way, I will use interchangeably the word lists and alphabet, but they mean the same thing, right? There is nothing about this. So I should say a few things about the references that I've indicated first. So there is a first proof of this result by Grichuk, hopefully I'm pronouncing it right, Bilo and Thue in 2011, and this result was using something called the left-handed local lemma, and was something like, really the main proof was 7 pages. Then a bit later they improved it using, Grichuk and other co-authored improved it using entropy compression, and now the proof is something like 5 pages. A bit later, I don't know who exactly, but using a technique called the power series method, it was again improved, and then the proof became much simpler. And finally, in 2020, I gave an even simpler proof of this, which takes something like half a page, and this is what I'm going to present in the next slide. So this is really the proof I want to present today. The proof of this result using this technique, which I'm going to call the counting argument for the sake of this presentation. Okay, so how am I going to prove this? Well, the first idea, as the name suggests, is instead of proving that there is at least one word of every length, I'm going to prove that there is a lot of them. Like I'm going to count them. So for this, I will just need to introduce a few notations. So I will fix my sequence of alphabet for the rest of these 2 slides. And I will write Cn, the set of square free words of length n that respects my sequence of alphabet. And now what I want to prove is the following lemma, which is that, the size of Cn plus 1 is always at least twice the size of Cn, which is way stronger than what we had before, right? In particular, this implies that the size of Cn is at least 2 to the n, because the empty word avoids squares, so there's at least one word of size 0. And clearly 2 to the n is larger than 1, so we have at least one word of every length, right? But somehow really this is actually a crucial part to introduce this particular lemma, because I'm going to provide a proof by induction of this lemma. And as often, this is really important for my induction to work, to have the good hypothesis, right? So like half of the idea of this proof is really to introduce the right lemma at some point. And now I need to do the proof of this lemma by induction. This is going to be the next slide. Hopefully I'm not going to go too fast. In my opinion, this is the most interesting things I have to say, the proof in the next slide. So if something is not clear, please interrupt me. Okay, so as I said, I want to prove by induction on n that the size of Cn plus 1 is at least twice the size of Cn. So let's just choose my induction hypothesis right now, so I don't have to think about it really anymore. What it means is now if I'm comparing Cn to smaller Cn minus j, then it, right, so Cn minus j is, the size of Cn minus j is at most the size of Cn divided by 2 to the j, right? Because I'm removing n letters, so it's just applying a few times my induction hypothesis. Okay, so we will use this in the end in some computation, but now I don't have to think about the fact that I'm doing an induction anymore. So now what's actually the idea of the proof? The idea of the proof is I'm going to take words from Cn, so I want square-free words which respect my alphabet of length n, and I want to look at what happens whenever I'm trying to adding the next letter. So I'm going to take a letter from my next alphabet, and I'm trying to add one letter from this alphabet. What happens? Well, somehow two things can happen. Either this is a square-free word, in which case it goes into Cn plus 1, or I will put it in B. B is just what I'm going to call the set of these bad extensions. Right? So I'm starting from a word from Cn, I'm adding a new letter from my alphabet, and for some reason something went wrong. Then I'm just going to put them in B. B like bad. Okay. Then by definition, the size of Cn plus 1 is exactly the size of Cn multiplied by the number of extension minus the bad extension. Somehow my hypothesis was that every alphabet is of size at least 4, so let's use it right now. So I know that the size of Cn plus 1 is at least 4 times the size of Cn minus the bad extension. So now my goal is going to be to upper bound the number of bad extensions. And for this, I will just partition my set into smaller sets, which I'm going to call Bi. So Bi is going to be the set of words from B that end with a square of period I, sorry. So in particular, I know that all of the words from B, they end with a square, because if something went wrong, it means that a square appeared, so it has to appear at the end. And now I'm just going to partition this set into this Bi, which means that B is the union of all the Bi. Right? So in particular, the size of B is at most the sum of the size of the Bi. Okay. Great, so now I want, so let me just use it in the equation on the top, just to make some progress. So now the size of Cn is at least 4 times the size of Cn minus the sum of the bad extensions. Okay, good. Now let's bound the size of Bi, and this is going to be the second important part of the argument. We will use a simple idea for this, in fact. So let's take W that belongs to one of the Bi. So this is W, it belongs to Bi, great. I know one thing about W, which is that it ends with a square of period I. Okay, so I have this square UU, such that the length of U is I. Great. Now let's look at the beginning of this word, by which I mean I'm taking all the words until the second occurrence of U. Well, in this word, which I'm going to call V, I know that there is no square, right? So this word, just by removing the last letter, I know that I've killed all the squares. So if I remove more than the last letter, then I've killed all the squares. So V is a square-free word, and it respects my alphabets. So V belongs to Cn plus 1 minus I. Now if I have one such V, can I get back the word W? Yes, I just need to take the I last letters of V and to repeat them. So basically it gives me a unique way to get back my word W from any word from Cn plus 1 minus I, which means that the size of Bi is at most the size of Cn plus 1 minus I. Yes?
So you said we should ask if we don't understand.
Yeah.
So
wait for the mic.
If you have a question, you should ask about the microphone.
you said we should ask a question if we don't understand. So peut-être c'est le décalage horaire, maybe it's the jet lag, but could you explain why V has to be square free? It seems to me that you may have many squares in one word, so simply removing, breaking up the square at the end, why is the remainder square free?
Yeah, so my definition of B was, I'm taking a word from Cn, and so Cn, it is square free, and I'm adding one more letter. So if I have a square, I know it's at the end and there is no other square. So now if I remove at least the last letter, then
it was the jet lag, thank you.
Yeah. Good you asked, anyway. Okay, so basically now I've done everything. I just need to use my three equations together and we will have the conclusion, the desired conclusion. So as I said, the size of BI is at most the size of Cn plus 1. Let's use my hypothesis up there. Since I'm removing I minus 1 letters, I know that this is at most the size of Cn divided by 2 to the I minus 1, right? Now I'm going to use it with the other equation, and this is done. So let me just, I've just copied the equation on the top. I will just replace size of the BI by the upper bound that I have on the size of the BI. And I'm just going to factorize by Cn to make it slightly more convenient. And this is what I get. And this is actually the most advanced part of the proof. You need to know that the sum of the 2 to the I is 2. And then you get that 2 to the minus I, sorry. And then you get that, yes, the size of Cn plus 1 is at least twice the size of Cn. And that's it, that's the proof. This proof, I think it's quite simple, but maybe if you haven't looked at this kind of problem, it's not that apparent that you would need other strong tools to do just similar things. Also, it relies on really, really simple arguments, which I think is quite convenient. Okay, let me say, well, other things now.
The last slide.
Yeah.
The last inequality should be equality.
Sorry?
The last inequality should be equality.
Right. But this is true as well, right? This is correct. I could be sharper. I will discuss sharpness of this proof in a while. We can go back to this comment. You're right. Okay, yeah, so maybe just to say a few words. This proof is in fact much more general than this. You can apply it to many other problems, and usually at the end you get an inequality, not an equality. That's why I went, yeah, I should have written an inequality, I agree with you. Okay, so let me just remind what we have just proven, which is, well, slightly stronger than this, but if all of my alphabet are of size at least 4, then there exists a square free word.
Excuse me, I hope you don't mind. What if the size of AI is 3? Is there, will the conclusion also hold?
Sorry.
Okay. What if the size of AI is 3? Will the conclusion also hold?
If the size of AI is what, sorry?
It's 3.
I will take it in 5 seconds. Okay. So this is what I've just proven, and this is the question that I'm going to ask. So what if the size of the alphabet is 3? Actually, we don't know. I will say a bit more about this later. And really this question, like 7 years ago, was my main motivation to look at this kind of techniques, which since then I've used to do a lot of other things, but I haven't been able to solve this question with it yet. But anyway. Okay, so I don't know what if the size is 3. Okay, let's talk about your other question, sharpness of the proof. Somehow there are some parts of this proof which are not sharp, where we could hope to improve it. Like, okay, if we look at my induction hypothesis, then somehow the first equation that I have on the top, I don't have really other choices than this. Again, when I define an plus 1, when I define b, somehow the second line of equation, it has to be what it is because the size of n plus 1 could be exactly 4 by my assumption. But now some parts are not sharp. In particular, so the first thing is I'm writing that b is the union of the bi. So the size of b is at most the sum of the size of the bi, which might not be true if some of the bi intersect each other, right? In this particular setting, it happens to be an inequality, in fact. I could replace this inequality by an equality because the way squares can intersect each other, this would mean I have a third smaller square, which is not in the end of the word, which would be a contradiction with my hypothesis. So I could make this an equality, but somehow there is no hope to improve this inequality. But now there is the one which is really interesting, which is this one. This one, like the argument is nice, but this is far from being sharp, this inequality. And so somehow if we want to improve this proof, for instance, if we want to prove something better than 2, like that the growth rate is at least, 2.3 or something like that, then we need to work on this part. So this is what I want to discuss a little bit in the next few minutes. So somehow I have this bound on the size of bi, which is not sharp. One thing to note is, somehow if I is large, I don't really care because I have this Power series, but now if for I don't know, 1000, this is going to be so small that, yeah, I mean, it's going to be some really, really small quantity. So if I want a good approximation of my growth rate, it doesn't really matter. The one that matters are when I is small, right? For I equal 1, 2, 3, 4, 5, then maybe I'm losing a lot in my inequalities because of this. So how can we improve this? And there are some techniques to improve this, which are, well, somehow, for this, you need to look at what precisely happened in the local behavior. And one way to do this is, okay, let's look at an approximation of my language, which is I'm going to look at words which avoid only short squares, right? I'm going to forbid only the short squares because they are the one which seems to be I need to look at. And now I'm forbidding only finitely many factors, so I can use automata theory, right? This is just a regular language, so I can compute an automaton, compute the growth rate associated with this automaton, and somehow I can find the growth rate of this language. And now I have this hope, which is this inequalities is not correct, but somehow this is what I want, what I wish to be correct. The size of Cn plus 1 should be larger than the size of Cn multiplied by the growth rate of words which avoid short squares, but now I also need to avoid the long squares, so for this I need to remove the bad extension that are due to large squares. So obviously this is not correct, because for this to be correct, somehow I would need here to have, in fact, the set of words without short squares, and not somehow it breaks something. But there are ways to fix this. Yes?
Sorry, in the first inequality, I is relating to n, right? It should be.
Yes, it should be for I smaller than n, but again, we don't really care. But yeah, you're correct. Like I could stop the sum at n. That's true. But somehow I want to do it for any n, so yeah. It's the same. Yeah. Okay, so I don't want to go into details, but now the idea is using just basic automata theory, linear algebra, you can find some weights. Instead of just counting the word, I'm going to give a different weight to different words. And I'm going to say that now the weight of a set of words is just the sum of the weight of the words. And now I can actually prove such an inequality using these weights. Like I could prove that the weight of Cn plus 1 is at least alpha L times the weight of Cn minus the bad extension. And all of this is using really the spectral radius of the automaton. You find the associated eigenvectors. I mean, everything is quite classical. We know how to do it efficiently with a computer. Everything is fine. Now, the only difficulty would be maybe the bijection that you need to use to bound the BI might be more complicated.
Okay, may I ask?
Yes.
About alpha L. If all of your alphabets are the same, that's very clear what is alpha L and how to compute it with an automata. But if all of your alphabets are different,
this is more complicated.
How do you compute it with an automata?
This is exactly the kind of details I don't want to talk about, but this is, yeah, this is more complicated. But the idea is the same. It's just, I mean, you have to put the ends on it and then just to do technical stuff, which are a bit annoying. But the idea is quite the same. Like
okay.
You need some extra ideas to make it work, but this is quite similar. Yeah. Anyway, the idea is in some sense I compute an approximation of my language. Now I can find the growth rate of this approximation, and now using this counting argument, I can prove that I don't need to remove too much, like all this bad extension. This is just something which can be taken to be really small, and I get the growth rate of the language I was really interested in. So you could do it by hand, compute small automaton by hand, or you could do it using a big computer and computing really large automaton for really large approximation of your language. And this is the kind of thing I've been doing. So this is what I will be talking about. Oh yeah, and I should say a small few words. Similar technique was already used by Kolpakov, then Kolpakov and Rao, and then Thue to obtain bounds on the growth of power-free languages. So there are some ideas which are really similar in this. Yes, okay. And so using this idea and some of the things I don't want to talk about because they are just really annoyingly technical, I can prove something like this, for instance, which, I mean, like it's really weak in some sense, but still I'm really happy about this, so I'm going to talk about it. So suppose all the alphabets are of size 3, which is really what I want to prove, but now I need some extra condition, which is that, well, all the alphabet belongs to 0, 1, 2, 3, right? So somehow, in total, I only have 4 different letters, but all the alphabet are of size 3. Then there are square-free words that respect this alphabet and which avoid squares. So there is something, again, against this intuition I was mentioning, which is somehow the only setting in which I can prove something is when the alphabet are close enough, right? If all of the alphabet look like each other, then I can prove something. But now if you make the alphabet more different, I will have more difficulties proving that it works, which is really counterintuitive. Maybe because of the technique I'm using, but still. So I'm not going to go into the detail of this proof, but somehow it uses some of the ideas that I've mentioned before, plus some technicalities because the alphabet is changing at every position, so you need to do some things. You cannot use linear algebra anymore, but you do something that looks like linear algebra, the standard linear algebra on automatons. And so what I do, I need to compute the approximation of the automaton that recognize words which do not contain squares of pair less than 22. And this automaton is quite big. So it has 1 billion states. In fact, it has more states than this, but I'm doing some kind of renaming. Like I can always assume that the last letter of my word is 0 up to renaming, and that the previous letter is 1 up to renaming. So somehow by doing this, I can divide the number of states by 24. So in fact, the automaton has 24 billion states, but you can use this trick to make it a bit smaller. It takes something like 7 GB in memory with a lot of optimization and 2 hours of computation. So yeah, this is, I mean, it already requires quite powerful machines to do it. But somehow something interesting about this technique is, well, you could replace 0, 1, 2, 3 by 0, 1, 2, 3, 4, and it should still work. The only thing is, now this is a kind of computer I don't have, so I cannot do it. But somehow it should work. Like, if the conjecture is true, then it should be able to prove it. And more than this, if the conjecture is true in general, like if you can just get rid of the second condition, then I should also, I mean, okay, and if another conjecture is true, which is that the growth rate of the language is the same, which seems to be true as well, then actually I could even prove it with this proof. It would just require something like 10 to the 7 GB of memory, which, I mean, it's a lot, but it's not a lot, like, you know, maybe in 20 years. So I don't know. Anyway, so yeah, there is this proof technique that might help solving this problem. I mean, obviously the better direction is to try a way to improve the technique first, but maybe we can just wait 20 years, I don't know. Okay, so this is what I wanted to say about the Thue choice number. There are other things I want to mention related to this proof technique. Because, as I said, I think for me the most interesting part of this talk is really this proof technique, which I like. And it can be applied to many different problems. So let me mention, for instance, this. So suppose you have an alphabet and a set of forbidden patterns. So I'm back to the more regular standard setting in combinatorics and right? I have one alphabet. I don't have a sequence of alphabet anymore. And suppose that there exists a positive real, which is solution of the following inequality, right? And somehow this inequality should be reminiscent of what we've seen, right? Like the size of A is 4. This geometric sum looks like 2 to the minus I, and the thing on the right looks like 2. So it's not exactly the same equation, but somehow this is really the same idea, and the proof relies on the same idea. Anyway, if you have a solution to this equation, then this language is not empty, and in particular, in fact, the growth of this language is at least x. Yeah. So how would you prove this? Well, again, you would fix the alphabet, the set of forbidden pattern, and now you would say, I want to count the number of words, right? So Cn is going to be the set of these words which avoid my forbidden set of factors. And now what I want to prove is that whenever I'm increasing this n by 1, then I'm multiplying the number of words by at least x. Yeah, which means in particular that I have at least x to the n words of length. At least x to the n words of length n, which means I have more than 0, which means I have at least 1, right? So great. This means that I have at least one word. In fact, if there is a solution to this equation, the solution x is always strictly larger than 1, except for a few general cases. So in fact, it gives you exponential growth, but I don't even need this. So how does the proof work? So the proof is going to be, I'm going to do it quickly, but this is the same as the one we've seen before. So you should be able to have some idea of what I'm doing. So I want to prove by induction that the size of Cn plus 1 is at least x times the size of Cn, right? So for this, I'm first using my induction hypothesis, as I know that when I'm removing j later, then I'm dividing by at least x to the j, right? Again, I want to look at what happens whenever I do an extension. So I take a word of length n which is valid, and I add the next letter. Now it could go wrong, in which case I'm going to put it in b, or it could still be valid, in which case it's just in Cn plus 1. So I have a similar equation, okay? And now I have to compute a bound on b. For this, I'm going to split it again, to decompose it, and I'm going to do it according to f. So bf, so for every forbidden pattern f, bf is the set of words from b that ends with an occurrence of this particular forbidden factor. Since I know that every word in b ends with a forbidden factor, the union of the bf is just b, so the size of b is at most the sum of the size of the bf, right? And now the idea is, again, exactly the same. Well, now suppose I have w inside bf. This means that w is just some words followed by f. So now if I know this word v, I can guess w uniquely, right? I can obtain w uniquely. And moreover, I know that since I've removed the last letter, I've removed all the occurrences of bad factors. So v belongs to Cn plus 1 minus size of f. And I have the following inequality, which is that the size of pf is at most the size of Cn plus 1 minus f. And now again, I just have to put all the equation together and it's going to give me what I want. Yeah, so let's use our induction hypothesis. So the size of bf is at most the size of Cn divided by x to the f minus 1. Great, let's put everything together. I'm factorizing by Cn. And now, you probably don't remember, but I do. My hypothesis was that this is larger than x. So now I can conclude. Okay, so the idea of the proof is really similar, and you can actually apply it to many different settings, this idea. The other thing is, now when I showed the previous slide, when you saw this condition that A minus this geometric sum, this series is at least x, it might look like it's coming from nowhere, but actually, you just, at the beginning, you don't know what the assumption is, you try to do the proof, and the assumption really comes naturally at the end. Like, you really don't have to guess the correct assumption. It just comes to, in the proof directly. Okay, so that's the proof. Okay, what I should say is proof of the same result was already known. There is one by Oshem using the Power Series method in 2016. I pretend that my proof is slightly simpler, but not that much. It's a good illustration of the technique, but like the proof using the Power Series method is not much more complicated, and I think it's nice as well. Okay, it's also stronger than results used by Miller and Pavlov recently to prove things about different properties on subshift. And in particular, they wanted something about the size of the subshift, the growth of the subshift. And the bounds that we obtain by doing this are much better than the one they have, so that is nice. You can apply it to different problems, which are, right now, if you look at it, it's not clear that it gives you anything interesting, this lemma, but you can apply it to actual sets of forbidden patterns and you might obtain interesting properties. Okay, so now I want just to finish to mention a few other applications. Yeah.
For the previous slide.
Yeah. Okay. Yes. Okay, maybe we can go back to it after.
No, he didn't show the product.
Okay, so I want just to mention quickly, I'm not going to give the definition, but we've seen that this argument, right, I've been using it mostly to say the set is non-empty, but in the proof, I always need to say the growth of the set is at least x to the n. So can we say something really interesting with this? Can we prove that the growth of some set of words is large? And so, for instance, there is a following setting. So I'm not going to give the definition, but I'm interested in the growth rate of the language of x3 words over the alphabet 1 to k. Right? Okay, that's a question. And there is a following conjecture by Thue from 2009, who gives like somehow a good, like a precise estimate of the growth of different languages. And the conjecture is that this should be true. So it was open for a while. Actually, it's still open, but I was able, with this technique I've mentioned, to prove at least one side of the conjecture, which is, yeah, the growth is indeed at least this. And since we expect it to be this means that you can use this counting argument to get really sharp bound on the growth of the languages you're looking at. And in this particular case, the proof is quite simple. Like, again, it's half a page, just like the one for squares. It's really not that complicated. So, yeah, this can be used to obtain this kind of result about the growth of the languages as well. And it's completely by hand. There is no computer involved in this, which might be obvious. But okay, so let me conclude by mentioning one last problem, which I think is nice. So this is a game between Anne and Ben. So at their turn, Anne and Ben, they are going to, so they share a word. There is a word which they share. And at their turn, each of them, they add a new letter at the end of the word. And Ben, he likes squares, so he wants to create squares. And Anne, she hates squares, so she has to forbid creating them. So somehow, if there is a square of length at least 4 that appears, then Ben wins. That's the rule. So let's look at this game over 2 letters, for instance. I'm going to give a strategy for Ben. So suppose Anne starts by playing 0, which, I mean, you can do with complete generality. Then the strategy of Ben is to play 0 as well. Now, Anne, she has 2 possibilities. She could play 0, but then Ben can play 0, and then there is a square of period 4, of length 4, sorry. So maybe Anne try to place 1, in which case, for instance, this strategy of Ben is going to play 0, and now there are still 2 possibilities for Anne. She could play 0, but in this case, Ben plays 1, and then we have the square 0, 0, 1, 0, 0, 1. Or she could play 1, but then she's lost immediately because there is a square 0, 1, 0, 1. So over 2 letters, Ben wins pretty easily. If you look at it over 3 letters, I think you can do it by hand. It's more complicated, like the tree is slightly larger, but you can do it by hand and drawing this kind of tree and checking that Ben also has a simple strategy with 3 letters. And using this technique called entropy compression, Grichuk and some of his co-authors prove that, in fact, if there is at least 6 letters, then Anne wins, which is not obvious, I think, right? So there is Ben which tries to create squares, and Anne, she has enough powers to just forbid all the squares. That's pretty nice. But still, now this is open. What's the correct value? Is this 4, 5, or 6? And I was able, using, again, this kind of technique I've mentioned. Now I need a big computation with my computer to prove that if there is at least 4 letters, then Anne has a winning strategy. Okay, so I think this is a nice question. I like this game, but yeah. Okay, let me conclude. So this counting argument, so a similar technique was already used by other people, which this technique was called the power series method. It was used by Bell and Go, Rampersad, Blanchet, Sardi, and Woodhouse, Oshem. But somehow there was, as the name suggests, there was some power series in it, which didn't help. And actually removing it made the proof simpler and also allowed me to generalize it to other objects. So actually I've been using this proof for graph coloring, hypergraph coloring, KSAT, tiling, subshift, and many other settings. So this idea that comes from combinatorics and words, we can actually use it in many other areas, which I think is quite nice. And yeah, for instance, this is a recent result I have. I have a theorem which is quite similar to the one I had before, which is, but this time I want to look at tilings over some groups. And now I'm looking at tilings over groups, and if I have this condition that relates the forbidden patterns, then I can make a tiling of my group. Right. So don't look at the details, but somehow you can use the same technique and the proof is not much more complicated. It's almost the same. Okay, so this is all I wanted to say. Some of what I want to say is maybe if you have some combinatorial problem with this kind of flavor, you should try to use this technique because it's not so complicated to use and it gives some interesting results. Yeah. So thank you for your attention.
Okay, so are there questions? And please wait for the microphone before asking your question. Okay, Gabriel.
Thank you. So the technique I would use to know if there are arbitrarily long words avoiding a set of forbidden words would be based on the classical automaton, which is essentially the Alcorasic automaton built on the trie of forbidden words. You can suppose that the forbidden words are minimal without loss of generality. And so when you build a trie of all these forbidden words and you build the automaton that avoids these words, either it has a cycle or it doesn't. And of course you have arbitrarily long words, if and only if the resulting automaton has a cycle. So there should be some relation between this and the counting technique, but it's not clear to me how to, given the set of forbidden words, how to predict by counting whether the resulting automaton will have a cycle. Can you apply this technique to directly give a threshold depending on the set of words, or it's completely unrelated?
Let me just put the result back. Notice something there. I'm not asking my set of forbidden patterns to be finite. To apply automata theory, you need the set of forbidden patterns to be finite. Right? So in particular, I can apply it to squares. You cannot apply automata theory to squares.
Okay.
Right. So this makes a huge difference.
Okay.
So I think that's the first part of the answer. You cannot apply it to the same kind of problems. Okay. Now, as you suggest, and this is what I was somehow hinting at the beginning, like you can use the two things together in some sense. Like you can use this discounting technique to forbid the infinitely many factors, but which are big and which do not play a big role, and then use automata theory to control the small factors, the small forbidden factors. And somehow by doing this, you can obtain something which might be really precise. Like in particular, if you say you want to forbid squares plus other factors, then I'm claiming that I have a decision algorithm for this. I mean, I have no written proof of it, but I know that I can prove it somehow. And the idea is really like, you will compute this big automaton at the beginning that include all the set of finite factors plus all the small squares, and then you use the counting technique to eliminate the large squares. And maybe you don't get, and at some point, because of the way it works, the power series get negligible if you go far enough, so it will work. In complete generality, it's not clear where it works and where it doesn't, because the power series might be not that well behaved and stuff like this, but somehow, yeah, like the most powerful thing is to use these two things together. They are not, somehow they are complementary, they're not doing the same thing.
Okay.
Right?
So in order to get this kind of estimates, apart from your technique, there's also entropy compression and Lovász local lemma. Can you say in some precise way that this technique is strictly stronger in all of those cases? Or
yes.
Do you have some cases where you cannot improve on the existing results using this?
So the first thing is, okay, so to answer this, so actually there are, okay. I think in this kind of settings, it should be stronger than the Lovász local lemma. I don't have any proof of this. Like it's a claim that I'm making, which is pretty bold. But for this kind of setting, it should be stronger than the Lovász local lemma. At least it is the case for all the application we have. But that might not be a good proof. Now for the entropy compression that you mentioned, there are actually two versions of the entropy compression. One of them is equivalent to the Lovász local lemma. And one of them somehow is equivalent to this counting argument. There is no proof of this. But it's really like you have the same power series that appear at some point, and you need to compute the same thing. And at least in some particular setting, there are proof of it. But in general, since we don't have a really general statement of this counting argument, it's really hard to say it's the same thing. And somehow, and in the same way, we don't have a general statement of the. But whenever you try to make a big framework, you get the exact same bound, the exact same condition with this version of the counting of entropy compression and the counting argument. Yeah, and entropy compression does not tell you anything about the size, about the growth of the language, right? It tells you that the language is not empty, but it doesn't tell you that it's large.
Thank you.
Okay. Oh, Pierre. Last question, I think. Yeah.
Thank you. Is there a hope that this argument says anything on non-amenable case?
So, sorry.
For example, in your theorem, you have amenability, which plays a role. Is there a hope to go beyond?
Well, you know, I'm wrong. I don't need amenable in the theorem. It's, well, yeah. Okay. Let me be more precise. So what I can prove is that if I look at the growth in terms of words or locally valid words, then I don't need amenability. Amenability allows me to say that the locally valid words has the same growth as the globally valid one. So it's really not about this proof. It's like about it's really about writing this instead of writing. If I was writing the complexity of my language is at least beta to the n, then I could remove amenability.
Thank you.
Okay, so thank you again.